blackboard with nothing else. Then the homework problems from this section, you should be able to set them up, but then you might need hints in between, and I will give you those hints in between. Everybody got it? So it's the example problems that really dictate what you should be able to do closed book on your own in front of the class. Okay? Okay. So that's one thing that I wanted to address. And then the other thing that I want to address is that I suggested using maxima. And David just emailed me that he was having some trouble with maxima.
Yeah, I got the maxima to give me the answers, but I was trying to figure out how they got the answers they got. Because maxima gave me the eigenvalues, the eigenfunctions. I understood how they got the determinant, because they got the same determinant.
Yeah.
But it's getting from the determinant to the.
I don't know how they do it. What I'm using maxima is just to give me answers.
Yeah.
Can you do like the same thing on Maple?
Because you told us
So
you
you
can
can
trying to work it out.
I mean, so the point here is that you should be able to do simple ones by hand, but at some point, I'm very much for using these to let
Maple,
you.
you need to load a package sheet for it.
Yeah, you have to
With linear
algebra.
with
Yeah.
capital L and capital, that one's obsolete.
Is it really?
You have to use
Is it
capital L linear, capital A algebra.
Okay, so look, Maple's powerful, Mathematica's powerful, there's a whole bunch of mathematical tools. You can use LabVIEW. LabVIEw does this in a breeze, all right? But, you know, Dale introduced this maxima to me. It's free, and it's simple, all right? And I don't have to keep buying all these things, you know, semester by semester.
I think the nice thing about Maple, if you use that here,
Yeah.
is that it gives you a matrix when you ask it for a matrix.
It
Whereas Maxima gives you a bunch of letters all crammed into one line.
I don't know. I've gotten used to maxima, whatever you are used to,
I
okay?
mean, just to see the answer, like when it comes up with a, like if you solve that A, H, H, A,
Yeah.
there's all these tons of square roots in there, and it's kind of hard to see what the matrix looks like when you get this long line.
Yeah, you
Instead of it being a matrix.
You have to know what you're doing. Yeah.
But I mean, you see it, and it's much easier to see it in Maple because it just spits it out as a matrix.
Yeah.
Instead of it spitting out bracket, bracket, letter numbers, comma, bracket, you know.
Okay. Yeah. Okay. I agree. Nothing's perfect, okay? Okay, so let's go. We're going to go into 6.2. And 6.2 is the infinite cube problem. Okay? And so I'm going to try to put it into the entire language, and in this case, the language is important, all right? Some of the things we're talking about. And basis and diagonalization and finding good basis and good quantum numbers and things like that. That language is important here, okay? So, example problem 6.2. Equals the infinite cube. All right, so the scoop is we have an infinite cube. The cube itself is not infinite, it's finite. It has finite length. It's a cube, so the lengths x, y, and z are at A. It begins at the origin. And the infinity is the potential outside of this thing. And we talked about this the same as the infinite 1D well, so we're all pretty familiar with this. And we're pretty familiar with the solutions, okay? All right, but this problem, what you might want to do is, so here's x, y, and z, and these are all A. This is A, that's A, and that's A, the height right there. All right, so here's the point, is that we have an infinite cube, but now they're going to introduce a perturbation, all right? And that perturbation is to put, they're going to add a well, let's start off, well, I'll draw it like this. They're going to put a little perturbation, and that perturbation is, we're going to add, all right, we're going to add an h prime equals v0 if 0 is less than x, which is less than a over 2, and 0 is less than y, which is less than a over 2. Which means you get figure 6.5, and so my drawing is pretty poor here, but you're going to have this little chunk carved out here. Okay, so it's essentially, this is V0. All All right, you've got a little potential block inside there. Okay? All right, so here's how you would start. The way you start doing quantum mechanics is you go, well, h times psi n equals E n psi n, right? And then you'd say, what's my Hamiltonian? My Hamiltonian is going to be equal to p squared over 2m plus v. And you say, okay, you know, that's kind of standard. But what we know from before, we solved already, v equals 0 on the inside. V inside equals 0. Right? In this case, h just went to p squared over 2m, which equals minus I h bar squared del squared in Cartesian coordinates, x, y, z. All right? And so what we'll now do is let's define this. Since we've already solved this problem, let's call this h0. And rewrite this as h0 times psi n0 equals E n0 psi n0. So this is the full language and notation that we're using for the perturbation theory. Right? And so if you were to write this, you minus sorry, there's no I there, right? Minus h bar squared.
That's h bar squared over 2m.
Over 2m del squared psi n0 equals E n0 psi n0. How do you go about solving that? Separation of variables, right? We did that. When you do separation of variables, what would happen?
Just need the basis.
Okay, so you essentially get 3 separate 1D well problems, one infinite well, remember? Okay? And the solution for those 3 separate 1D well problems is the 1D solution. Right? Then, what is the total solution? So we would do separation of variables, and then we would do something like this. We would say psi of n is really psi of nx, ny, and nz. And that would equal equation 6.31, but it's psi 0. All right, and it looks very familiar. I'll just write it once. 2 over a to the 3 halves. And then it's going to be sine nx pi over a times x, and sine ny pi y over a, and then sine nz pi z over a. All right, so there's no big surprise there, and what we've got here is that E of nx, ny, and z, 0, equals, we've used this all the time, pi squared, h bar squared over 2m, a squared, and nx squared plus ny squared plus nz squared. I mean, it's quite literally the 3 separable solutions for each dimension. Okay? Now, what are these solutions right here? What do I know about these? These are separable solutions to Schrodinger's equation. All right, so they form a
Complete basis.
They form a complete basis set. So we have a complete basis set. You know, we can expand any answer in terms of that complete basis set. All right, and right now, for as far as we're talking about, nx, ny, and nz are good quantum numbers. They completely describe our system and the energy exactly right. All right, so what we're going to do then is we're going to look at, so let me just see for a second. Okay. The first the ground state. What is the ground state of this? Okay, the ground state is always the lowest energy,
But n equals
non-zero wave function.
So n has to equal 1 for all three.
So it has to be 1, 1, 1. So it's psi n x equals 1, and y equals 1, and z equals 1. All right, and it has an energy, we'll call that E1110. All right, how many states are there?
Three.
It's only one state, right? Remember, the wave function is the multiplication of the three, but when you multiply them all together, it's one state. All right, so that's one state with everything n equals 1. All right, so if I want to then, what I want to do now is, okay, I say, now let's do the problem we want. Let's do h equals p squared over 2m plus b. All right, and so what we're going to do is let's have this equal to h0 plus h prime, and so we're going to treat the potential as a perturbation. Right? So what we're now going to say is, look, this is a harder problem to solve, p squared over 2m plus b. It's a very difficult problem. And so what we're going to do is, instead of trying to solve this exactly,
So we already know what the h0 is, because we just solved that out.
right, we're going to try to solve this using perturbation theory. All right, and what we say in perturbation theory is that the results we got En, I sometimes put the prime like this, is going to equal En0 plus En1 plus En2 plus so on. And I'll say that psi n prime equals psi n0 plus psi n1 plus so on. Okay, so in other words, maybe I should write this. So what I'm really looking for to solve is h total prime times psi n prime equals En prime psi n prime. So let's call this h total prime. So let's define this as h total prime. And therefore, this is the real problem I'm trying to solve, but it's too difficult. But it's too difficult. All right, so what we're going to do is we're going to do perturbation theory. All right, and what perturbation theory says is this En prime right there, this perturbed total eigenenergy, is going to equal to En0, which is the unperturbed energy, plus all these corrections. This is the first order correction, that's the second order correction. And that the solution to this too difficult problem, the eigenfunction psi n primes, are going to equal a combination of the unperturbed psi n's plus all these corrections. All right? Now what we have is now we just have the machinery to do it. All right? So here we go. Generally speaking, we only go up to this first order correction. And what do we know for this? We know that En1 is equal to psi n0 h prime psi n0. And if we wanted, we could find this one. Psi n1 equals, it's going to be the summation of m not equal to n. And it's going to be psi n0 h prime psi n0, all divided by E m minus En all times ket psi m 0. Okay.
And minus.
Isn't it n minus n?
It's n minus, yes.
Yeah, because n will.
Yeah.
Because En will have, well, technically have the higher
Higher,
energy,
yeah.
so you wanna have,
Okay.
If everybody's like
Yeah, yeah, everybody's doing that. But look, this is what we're doing. So we've done all the machinery, and this is all we're doing, okay? And then we talked about what this is in terms of an overlap, and we found out how much the Hamiltonian changes psi n, and then how much it overlaps with psi m. Okay, so what we do is this. We have to find, the goal in this problem was to find En1. All right, now, for En equals the ground state, which is Nx, well, which is a 1, 1, 1 for Nx and Y and Z1. We go and we just write out the answer. It's going to be psi 1, 1, 1, 0, H prime, psi 1, 1, 1, 0. Everybody agree? Can we use this, by the way, this is for non-degenerate degenerate perturbation theory. Can we use non-degenerate perturbation theory for n equals 1?
yes, because it's not in general.
It's non-degenerate, okay?